Good afternoon, everybody. Welcome to today's chem class, today's chem lesson. We are going to talk about branched carbon chains today. The last lesson we had, we looked at simple carbon chains using tables P and Q to tell what the number of carbons was and how many bonds there would be in it, right? Would there be any single bonds, double bonds, triple bonds? So we looked at something like heptane. We looked at something like heptane and broke it down using table P and Q to find out that this means 7 carbons and this means single bonds, which means that our drawing for heptane should look like this. All carbons, 7 carbons, single bonded with hydrogens to fill in the rest of the bonds, right? Every carbon getting 4 total bonds. Today we're going to look at what makes these a little bit more complicated by adding branches and looking at how that is going to affect our carbon chain. For example, if I do that, that's a totally different molecule, and we're going to learn how to deal with a chain that then has a branch coming off of it. Hold on for a question here. Some stuff on the homework that I don't remember going over. Are we doing that this week? Yes. If there's anything that was missed on the homework for yesterday, we're definitely going to cover it this week. It's probably just a definition that I misjudged by a day. So, not all carbon chains exist in a straight line, right? All the ones we did last week were straight line chains, but that was a basic introduction, right? There are some chains that have branches, which means, just like I showed you before, carbon chain with a offshoot, with a literal branch coming off of it. When we talk about these branches, we're going to reintroduce the idea of an isomer, which are compounds with the same chemical formula. So the same formula would be, but different structures, right? So the same formula, but different structures. They're going to have the same number of C's and H's, the same number of all their atoms, but they're going to be arranged in a different way. And I'm using this one for a very specific reason, which will show up in a second. When we're looking at naming a branch, we're going to use the prefixes that we had before, the prefixes on table P, and we're going to use the ending, the suffix, instead of taking ein, een, or ein from table Q, we're going to use the suffix il to name the branch. So, for example, if we're looking at this, if we're looking at this structure, we have 5 carbon chains, right? 5 carbons all single bonded together. This would be pentane, right? Just this piece here. This is pentane. But it's more than just pentane. It's got these 2 carbons coming off in a branch. So we need to name these 2 carbons. And if we look at the prefixes on table P, 2 carbons would be eth, eth. And the suffix for a branch would be il. So this is going to be ethyl pentane. But ethyl pentane isn't quite enough. We need to make note of which carbon the chain is on. So 1, 2, 3. This is on the 3rd carbon, so it's 3-ethyl pentane. When you're looking at an organic name, we're looking at back to front. we want to build it from back to front. So we would start by drawing pentane, 5 carbons, all single bonded. Then we would look at ethyl and know that we have 2 carbons branching off. And we would know where to put that because of the number in front. So we know to put that here on the 3rd carbon. When we talk about isomers, I'm just going to move this over. 3. Oh, that's too light. Ethyl. And then the pentane came in blue. Branches only have single bonds. Yes, for us, when we're looking at branched carbons here, right? When we're looking at this, we are not going to have any branches with double bonds or triple bonds. They can exist, but we are not going to see them. You could, Samantha, put the branch underneath coming down. That's also fine, as long as it's attached to the 3rd carbon. Right, so this is fine, and if you take it and you flip it upside down, right, and put these 2 underneath, that's also fine. Then I want to draw up for us our heptane like we had before. Hept is 7 carbons. 2, 3, 4, 5, 6, 7. All single bonded with hydrogens to fill in those other spots. If we look at these 2 things, if we look at heptane and 3-ethylpentane, they have 7 carbons and 16 hydrogens. Right, 7 carbons, 1, 2, 3, 4, 5, 6, 7 on top, 8, 9, 10, 11, 12, 13, 14, 15, 16. And if we look here, we've got 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Right. I'm sorry, YouTube. Why are you being weird to me right now? Why are you dropping frames? I'm sorry, everybody. Give me 1 second. For some reason, I'm losing video. Okay, I don't know if I could fix that. Alright, that's fine. I will redo this if I have to later. So, when we look at heptane and 3-ethylpentane, these things are isomers of each other. Right? They have the same formula. They are both C7H16, but this way of drawing it, right, drawing it like heptane, is very different than drawing it like 3-ethylpentane. Right? 7 in a row is different from 5 in a row with 2 offshooting. If I wanted to now do a new one, if I wanted to take this example, 4-methylhexane, and draw that out, I would take hexane first, right, back to front. Hexane, I know, is 6 carbons, all single bonded. So I would put 6 carbons in a row, all single bonded. Then I would go right back to front still, and I would say methyl, looking at table P, that's 1 carbon. The YL tells me it's a branch. So I've got 1 carbon that I'm going to attach somewhere. And this 4 is going to tell me it goes on the 4th carbon. 1, 2, 3, 4. Branch of 1 carbon. Ooh, let's make a nicer C there. Branch of 1 carbon. and then fill in all of my hydrogens. And that is 4-methylhexane. Right? Hexane with a methyl branch, right? 1 carbon, coming off of the 4th carbon in the chain. Right. As far as Samantha's question from before, this picture is exactly the same as this picture, right? Including the carbon underneath. That's exactly the same. If you put it above or below, it does not make a difference. Right. So with branched carbons, there's some vocab words we want to discuss here. There's 2 vocab words that we want to talk about. And the 2 vocab words are saturated and unsaturated. Are we only going to deal with hydrocarbons? No, we will do other things. We're just building up to them. So we're going to add functional groups either tomorrow or Wednesday, and make these a little bit more complex, right? We're kind of building in complexity as we go. Right. So saturated and unsaturated. Saturated is going to be something that has all single bonds. Right, so that's going to be our alkanes. And unsaturated means at least 1 double or triple bond. So that's going to be our enes and ynes. So it's just a way of classifying. So when we look at, for example, this carbon chain, this is an unsaturated carbon chain. Right? This has room for more hydrogens. Yes, Nicole, that is correct. Right, so if we're looking here, this is meth eth bute pro. No, this is butene, 1-butene. Right. If we look at this, there could be more hydrogens. Right. Saturated. The word saturated doesn't change in its definition here. Saturated means to be full of. Right, so if you have a sponge that is saturated with water, it's full of water. If we talk about a solution, a saturated solution, it's full of salt, holding as much salt as it can. Right? A saturated hydrocarbon is holding as many H's as it can. So this is not holding as many H's as it can because of this double bond. It could look like this. If it didn't have the double bond, it can hold an extra H here and an extra H here. Right? This H and this H are gone when this double bond exists. So saturated is going to mean the same thing that it does, full of, and in this case, it's H's. So this is unsaturated because it could have more H's. This is saturated because it has as many H's as it possibly can. questions, comments, or concerns there? What if it doesn't have... So, you can't be unsaturated if there are no double or single bonds. Or sorry, if there are no double or triple bonds. So, in order to be unsaturated, you must have at least one double or triple bond in it. Because if they're all single bonds, it's going to be full of H's the way it should be, or should in air quotes. Right? If there's all single bonds, everything else is an H. All right. And with that, I've got a bunch of practice for us again. If there are multiple branches in a chain, we're going to see that actually right here. Our last example is multiple branches in a chain. So just hold that for a second, Nicole. We've got the following branched organic molecules, and we're going to draw these out. Again, when you look at something like this, when you look at 3-propyl 3-octene, you want to draw it out from back to front. You want to start with the base, right, which is our octene, and then move outwards and add things to it, right? This piece that I'm underlining here, these pieces are the bases of our building, right? We're starting with a foundation of a carbon chain, and then we're adding stuff to it. All the rest is additions to our basic carbon chain. So when I look at 3-propyl 3-octene, I'm going to start by drawing octene. Oct is the prefix for 8, so I'm going to put 8 carbons in a row. Ene means that there's a double bond. The 3 tells me I'm going to put that double bond on the 3rd carbon. First, second, third, double bond. If I was just drawing 3-octene, I would start filling in H's. But there's more. There's 3-propyl 3-octene. And so I keep going. Prop is the prefix for 3 carbons. Hold, please. Why is YouTube doing this to me? Stop that. Why is YouTube doing this to me? All right. Well, prop is the prefix for 3 carbons. So I'm going to have a 3-carbon branch. That's where the YL comes in, right? A 3-carbon branch. And the place I'm going to put that, again, is determined by the number. I'm going to put it on the 3rd carbon. 1, 2, 3. And then I'm going to put this branch of 1, 2, 3 carbons. Now that I've accounted for all of my pieces, I'm going to make sure every carbon has 4 bonds by connecting H's to my carbons. Right, so I've got 8 carbons in a row, a double bond on the 3rd carbon. That's my 3-octene. A branch of 3 extra carbons coming off of the 3rd carbon. 3-propyl. Together I've got 3-propyl, 3-octene. If I wanted to try another, I would look at 7-ethyl-2-decyne. Again, we're going to work our way from back to front. So I'm going to start by drawing the 2-decyne. Dec is the prefix for 10 carbons. Ine means that there's a triple bond on the second carbon, right? That's what that 2 is telling us. So on my second carbon, first, second, put a triple bond. And this is the start of my 2-decyne. But it's not just 2-decyne. It's 7-ethyl 2-decyne. And so I need to put a branch of 2 carbons on the 7th carbon. So I'm going to count. First, second, third, fourth, fifth, sixth, 7th carbon. And I'm going to put a branch of 2 carbons coming off of there. Then I'm going to go back and fill in all of my hydrogens to correctly draw 7-ethyl 2-decyne. I'm going to move a little bit faster now, drawing the next one. 3-methyl 2-pentene. I'm going to work my way from back to front, starting with the 2-pentene, 5 carbons, double bond on the second one, and on the third carbon, a branch of 1 additional carbon. Filling in all my H's so that every carbon has 4 lines touching it. This here is 3-methyl 2-pentene. Next up is going to be 2-ethyl heptane, starting by drawing the heptane. 7 carbons in a row, but not just 7 carbons in a row. It's got an ethyl, so 2 carbons branching off of the second carbon. Filling in all my H's to make sure that every carbon has 4 lines touching it. Gives me 2-ethyl heptane. Next up, we're going to look at 2-methyl 1-propene. 1-propene is going to be 3 carbons with a double bond on the first. 2-methyl 1-propene means on the second carbon, I'm going to put a branch of 1 additional carbon. And then fill in my H's to make sure every carbon has 4 lines touching it. Six-methyl 4-nonine. I'm going to start by drawing nonine, which is 9 carbons in a row. 9 carbons in a row for the non. Ine means triple bond. 4 means on the fourth. First, second, third, fourth. Triple bond. Then on the 6th carbon, a branch of 1 additional. 1, 2, 3, 4, 5, 6. 1 additional. Filling in all of my H's. Gives me 6-methyl 4-nonine. One methyl butane is going to be 4 carbons in a row, all single bonded. And on the first carbon, a branch of 1 additional carbon. All right, here's the butane and the 1-methyl. The last one shows something that has 2 branches. Right? And that's fine. There's nothing wrong with having multiple branches on a carbon chain. That's totally possible. You could have a branch on every piece of the carbon chain if you so wanted to. right? What we're going to do is, again, start from back to front. So we're going to draw one hexine. So 6 carbons in a row. A triple bond on the first carbon. A methyl branch on the third carbon. 1, 2, 3. That's 1 additional carbon. And an ethyl on the fourth carbon. So that's 2 additional carbons. It doesn't matter if you put one up and one down, or both up or both down, as long as each carbon has 4 lines touching it. This would be 4 ethyl, 3 methyl, hexine. You do not need to write the H's in, right? You don't need to physically write an H on each of these lines, but you do definitely need to have these lines present. Hold, I see the flood of questions. I will get there in a second. Okay, so from the top, you do not need to draw the H's. I can repeat 1-methylbutane. Give me 1 second. You can have it where one goes up and one goes down, right? If I wanted to redraw this, and put the ethyl going down, that's totally fine. There's nothing wrong with that. Carbon, carbon. That is totally acceptable. There's nothing wrong with this drawing. You can have one up, one down, both going up, both going down. It doesn't matter if they're up or down. What really matters is the carbons that they are placed on. Why is it methylbutane and not methylbutane with a dash in between? Like, why is there no dash there? I think it's to differentiate the numbers, right? Think about it the opposite way. If you had 7 ethyl to decyne all together like that, with the numbers just kind of squished into the letters, it would look weird. So I think they do this with the dashes more to separate out the numbers than any other reason. Right, and then 1-methylbutane over again looks like this. And if something about 1-methylbutane looks weird to you, it's because it should look weird. And we are going to talk about why that's weird and how to fix it next time. Right? For now, the branches do not bond to each other. That is a good point, right? If you have 2 branches next to each other, for example, if I have this and this, let's make that a better line. We're not making a box. We're not like, these do not connect. That is incorrect. We do not want that. These have 2. This one has its own hydrogen coming this way and another different hydrogen over there, right? They're not going to connect to each other. Why do branches form and not just connect to the main chain? It depends on a lot of different factors. That goes into some of the more advanced organic chem. So for example, if I had, right, one reason why they would attach is if this was a double bond here, right? If this originally started as a double bond and a branch was gonna form, it's easier for a branch to kind of connect here and here and break off this double bond, snap, and allow for something to add here and here. We're going to talk about reactions later in the unit. We'll talk about like how things get added on, how they get taken off of carbon chains. Ooh, so Nicole asks a good question. In doing the inverse and naming a diagram, does it matter if you write 3-methyl-4-ethyl? Right? 3-methyl-4-ethyl versus the other way around. 3-methyl-4-ethyl 1-hexyne. Or if I do this, 4-ethyl 3-methyl 1-hexyne. It doesn't matter for drawing it out, right? If you draw either of these things, you're going to get the same picture. But there is a correct way of naming it, just so that for longer molecules, there aren't 100 different names for them. And we'll talk about that tomorrow when we talk about naming, right? When we look at pictures and go to naming them. All right. So I'm going to transition us into office hours. You can find the link to our Google Meet on Google Classroom. And if you have any questions, comments, or concerns, come check in with me in office hours, and I will answer any questions that you still have. And tomorrow, we'll keep going. All right. Have a fantastic day, everybody.